Alright, today I'm going to be talking about patterns in addition equations. And I'm going to start off just by showing you the, I guess you could call it the rule for this pattern. But here it is. If you know the notation, you should be able to pause this video right now and just, figure it out. But I am going to say don't pause just yet, because if you do pause and do this and figure out the pattern for your own, that's great. And I'm really happy because it's probably the best way to learn it. But towards the end of this video, I'm going to be talking about variations of this pattern. So this isn't the only one in this video. So if you do pause, which I suggest you do, and try and figure this out on your own, make sure you come back and watch the rest of the video, because it will variate. This pattern will. But it's a cool pattern. It works every time, so I do suggest if you know the notation, then go ahead and pause now. Otherwise, keep watching, and I'll try and explain it out as best I can. Alright, first off, let me move this off to the corner a little. I'm going to be referring to it in the video, but if you're watching the low resolution or the low definition version of this video, you may not be able to completely read all this right now because it's so small. But as I said earlier, you can pause it earlier on in the video, and it should be large enough for you to read. So let's go ahead and start off by writing this equation, x plus y equals z. And I'm just going to plug in random numbers for that. So it's strange, I seem to have a block right there. Okay. No, that's... Alright, I see what's going on. Okay. Now it should work. Good. Alright. 32 plus 57 equals 89. So what we're going to do according to this is we're going to sum up this number, the number x, right? Okay, so 3 plus 2 is 5. And then we do the same thing with the number y. So 5 plus 7 is 12. And we will do it again with z on this side of the equation. So 8 plus 9, that is 17. Alright, now we add these two together. Okay, c, x, y. So 5 plus 12, 17 equals 17. And this part can be explained with algebra. I mean, this is just simple how addition works. But the part that can't be explained with algebra is coming up. I'll show you that in a second. I have to use a higher number example, one that carries over more. But for now, I'll just show this. And then we take the infinite sum, so we keep applying that function to these numbers now. So 17, 1 plus 7 is 8. 1 plus 7 is 8. And then 8 plus 0, so it'd keep becoming 8. So that's the end of the function. 8 equals 8. That is a true statement, so the rule does apply. But let me show you with larger numbers. This is the part where it starts not making sense. Like, oh, algebra can't explain this, it can't. So we'll say 98 plus 75. Right. So 5 plus 8 is, I'm sorry, I was doing my math in my head. 98 plus 75 is 173. Alright, so these numbers carried over. Taking the digits here and adding them isn't going to give you the same result as adding these three. So 9 plus 8, 17. 7 plus 5, 12. And 1 plus 7 plus 3 is 11. Alright, then we have to add these two. 17 plus 12 is 29. 11 stays 11. Right? 2 plus 9, it's 11. and 11 is 11, of course. And then 1 plus 1 is 2, 1 plus 1 is 2. And the reason I make you go this extra step of infinitely adding these is because sometimes you'll end up with something like 10 over here on this side and 1 over here. So it would seem that they're not the same, but once you do 1 plus 0, they are the same. So that's why I'm adding the 11 together to get the 2. Just standard protocol, really. But as you can see, the pattern works, and this works with all addition. You're always going to have the sum of these end up being the same. And with that said, if I were to rearrange these numbers, like perhaps change the 75 to a 57, right? Then I still get 17 and 12, which still gets me 29, which still gets me 11, which still gets me 2. But I don't have 173 anymore. I actually now have 98 plus 57, which is 155. I'm sorry, 153. No, 155. I did that right. You'll have to excuse me. It's 3 in the morning. I'm really tired. Alright, 155. And 5 plus 5 plus 1 is 11. 1 plus 1 is 2. So, you can see that it always works when you rearrange these numbers as well. Pretty cool. The other interesting thing is you can, let me move this whole problem over. It doesn't just have to be x plus y equals z. It could be x plus y equals z plus w for the rule on the left. So if we were to make this, say, instead of 155, we could make it something like 142 plus 13. And this in itself is a true algebraic statement. So now we have 9 plus 8, which is 17, 5 plus 7, which is 12, 1 plus 4 plus 2, let me put the equal sign, 1 plus 4 plus 2, which is 7, and 1 plus 3, which is 4. Now if we add these two together, 17 plus 12 is 29. Alright, I probably shouldn't have used an equal sign, but for now, I don't have the notation for that. I'll probably come up with one soon. 7 plus 4 is 11, right? This is why we have to do the infinite sum, because 29 does not equal 11, right? So 2 plus 9 is 11, 11. 1 plus 1 is 2, 1 plus 1 is 2, checks out. And the other interesting variation is using digit notation. Let me give you an example of 93 plus 78 equals, and that would be 171. And according to digit notation, 171, let me delete this, is the same thing as 16011, right? So instead of saying 93 plus 78 equals 171, we'll say 93 plus 78 equals 16011. That's a 3-digit number, right? If you haven't seen the digit notation video, you might want to go watch that after this. But alright, 9 plus 3 is 12. 7 plus 8 is 15. 1 plus 6 plus 11 is 18. 12 plus 15 is 27. And we still have 18 here. 2 plus 7 is 9. 1 plus 8 is 9. Always checks out every time. So here is the rule again. Let me enlarge that if anyone wants to see that full screen. Here it is, and it works every time. So I hope you guys enjoyed this video, and I hope it intrigued you, and allowed you to learn more about addition, which is always a goal at Decimology.com, to learn more about math and the patterns in it. So this is pretty cool. And if you have questions, feel free to email me. If you find an exception to this rule, which I still haven't found, I'd love to hear about it. And if you find another pattern even, let me know. Also, if you ever find an algebraic way of explaining any of my patterns, please email me. I'd love to know so I can feature that video and then void the pattern. It won't really be voided as a pattern itself, it still is a pattern, but it will not be considered pure decimology. I'd like to think of decimology as the study of all patterns in math, so I would consider it patternology, decimology, but not non-algebraic patterns, which is what I'm really after. But as of now, I don't have an algebraic explanation for this. The first example I gave at the start of the video can be explained, but once you start carrying numbers over, it gets really hazy, and I've started to work it out, but I still can't find an algebraic explanation. So as far as I'm concerned for now, this rule here is decimology. It is non-algebraic. Alright, until next time guys, see ya.